Very good. Thank you very much for inviting me to discuss this very interesting paper. I'm the last thing between you and skiing, so I'm going to try to keep it as painless as possible. This is a fascinating paper along very many dimensions, and it's a very rich one. It addresses a very fundamental question in corporate finance, which is what is the optimal design of securities under asymmetric information, a question that was raised by Major and Maslow in 1984, and we're still debating this question. And the intuition that was behind Major and Maslow, as we know, was that debt is better because it's less sensitive than equity when insiders are more informed on the value of the securities rather than the outsider. This is the insider-seller problem. There is an equivalent outsider-informed problem that generates a quite different conclusion. So we're going to focus on the informed seller problem here. And under this situation, the firms then would pool under the Major and Maslow intuition until they reach that capacity, and then they would switch to equity. As I said a moment ago, a lot of discussion went on over time in trying to understand what are the conditions under which this theory will hold. This paper takes a new tack to this question and asks the question of what the security design problem will look like when investors are ambiguity averse as opposed to standard subjective expected utility maximizers. Now, let's be very clear. This is a very important and very difficult task. And the reason is because we need to develop a completely different set of theoretical tools in order to address this question in a rigorous way. And I would like to commend the authors for picking up this task. I think that the paper has two main contributions. One is to develop these theoretical tools in order to address these questions. And the second, and apply these tools to the security design problem. So what I'm going to do in my discussion is focus more on the methodological aspect because they are key in understanding the results of the paper. I'm going to mention very briefly where I think is the main contribution in terms of the application to the security design problem. So let me step back for a moment so that we understand what is the big picture here. Ambiguity aversion was, broadly speaking, developed as a way to model a situation where decision makers do not know the probability distribution involved in their decision-making process. This is the distinction between risk and uncertainty. Risk is when I know the probability distribution. I flip a coin where I know it's a fair coin, as opposed to uncertainties where I do not know whether the coin is fair. So I don't know what the probability distribution involved are. And it was developed to explain a certain paradox that emerged in experiments in the decision making. And the most important one is the Ellsberg Paradox. Let me just mention a little bit what the Ellsberg Paradox is, because it becomes important in what I'm going to say in a moment. One way to present the Ellsberg Paradox is the following one. There are two urns. They both contain 100 balls. One urn has 50 red balls, and the other one has 50 blue balls. So this is the known urn because I know the distribution. The second urn, the unknown urn, has a blue and red only, so I know there are only red and blue, but I don't know what the composition is. So now I give the decision maker the following question. I give you the following choice. I give you $100 if you draw a blue ball. So the question is, where do you want to draw the ball from? From the known urn, or from the unknown urn? And in most cases, the decision maker prefers to draw the ball from the known urn. Now, if that is the case, it reveals that the decision maker must be thinking there are more red balls in the other urn. But then I corner the decision maker because now I offer $100 if you draw a red ball. If you were to think there are a red ball here, you need to choose the ball from here, but you don't. You again go back to the to the known urn. And that's the paradox. So how do we solve the paradox? One way to solve the paradox is to think that you don't have a single prior on the unknown urn, but you have multiple which straddle one half. Let's think about this way. And then nature works against you in a way that when I'm confronted with this lottery, the nature puts more red balls here. When I'm confronted with this lottery, then the nature puts more blue balls here. And that's one way to make sense of or explain this paradox. So how the next step is, under subjective expected utility, the decision maker has a prior mu and evaluates the utility according to the standard expected utility approach. The alternative paradigm is the minimum expected utility approach. And this follows from the uncertainty aversion axiom, says that if you have two lotteries, I'm indifferent between these two lotteries, I prefer a randomization over these two lotteries weekly, this should be a week, over each one of the original lottery. This action is what generates uncertainty edging, because it might be possible that my uncertainty over this lottery is reduced as opposed to the uncertainty I have on each individual lottery that is at the base of the choice problem. So what Gilboa and Marshall show is that if that is the case, then we can describe the behavior of the agents as if they have not a single prior, but multiple priors. And the utility that receives the index is the means of the expected utility after each prior is used. So basically, I take each prior in the set, and I will pick the prior that minimizes my expected utility. Okay, so what is important here? The set M represents the set of beliefs and is a representation of the preferences of the decision maker. And the bigger the set, the bigger the subjective uncertainty that the decision maker perceives in the decision-making problem. Now, what is important here, if M boils down to one prior, then we are back to the original subjective expected utility. Okay, so now we go to the model. With this in the background. So this is a standard security design setting with the uncertainty averse investors. There is a future cash flow Z over a certain set. And the issuer knows the probability distribution over these possible outcomes. So F belongs to the simplex over the set Z. And the investor faces uncertainty. So the question is how to describe the core belief set. And this core belief set is only the possible distribution in the simplex such that this inequality is realized. Okay? So this parameter mu represents the degree of uncertainty that the decision maker faces in a decision-making problem. This again is the subjective uncertainty around a certain reference probability G that the decision maker has. In some literature, this is a way to describe a model uncertainty, in the sense that I think the model is G, but I'm uncertain what the real model is, and I created this a ball around the G where my uncertainty lies. Okay, so graphically, that's what the set B looks like. Now, this set is kinked because of the particular function. We take the absolute values here, but you can use other criteria to define B. For example, you can use relative entropy, and then you can smooth out this set. Now, what is important here, I'm not going to talk too much about the results, but as a bearing into that, in this set, I allow a fair amount of freedom on the structure of of the distributions that are allowable. For example, in this region, the standard monotonic lateral ratio property holds, and we know that that should be the optimal security. In this region, the MLRP is violated, so I should expect different securities. I don't have all this fancy graphing that we saw a moment ago, but what I think is the interesting part is the region that come up in between, because in the standard security design problem, equity is really never optimal. You have kinked securities that are the optimal security when MLRP is violated. So I think this is an interesting feature of the results. Okay, so let me get to what I think are the issues that we need to address here. In the current formulation, uncertainty and uncertainty aversion of the decision maker is deeply interconnected with the way the authors think about asymmetric information. So let me take this point in this way. So we know that if the core belief set is a singleton, the agents are standard subjective expected utility decision makers. So now if here I set nu is equal to 0, so then the core belief set B collapses to G. Okay? So this is a situation in which the agent is 100% sure about the wrong model unless F is equal to G. Okay? So, but then if I require the consistency that F is equal to G, then there is really not asymmetric information. So the tension here is that it's hard to disentangle what is uncertainty aversion from what is asymmetric information. In a way, it's not really a model of asymmetric information the way we usually think about it. So we need to do some thinking about it, which is critical because I want to be able to model asymmetric information in the context of uncertainty aversion. Now, the second point has to do with the notion of equilibrium. And what is the complication here? The standard uncertainty aversion literature has been developed in the context of games against nature. So I am a decision maker, and I face a decision problem. Nature takes certain work according to certain laws, and I assume that the decision maker takes the stand that has to make decision under the most adverse circumstances. Here we go one step past that because it's no longer a game against nature, but it's a game against another strategic player. So I add a layer of complexities that have to be dealt with. So let's just as a reference go back to the standard expected utility framework. The equivalent is a signaling game. In a signaling game, I have a set of types, and the informed agent knows the type. The uninformed agent has a prior on this set. The informed agent takes an action. The informed agents update the belief. This is the learning process. And then the uninformed agent takes another action, and then outcomes are realized. So the notion of equilibrium we use here is that agent maximizes the subjective expected utility, and update follows the Bayes rule whenever possible. Now we know that this whenever possible creates a number of complications that leads to refinements, but again, we're going to leave it like this. Okay, so let's get to the model here. So after receiving a security offer, the uninformed agent reevaluates the set of models and get this set B of S, and then value the security minimizing over the possible distribution F in this new set. And the equilibrium is determined in this way. So the key issue here is how to define the set of admissible types. And the way this type is defined is if I see a security offer S, okay, I am restricting the possible types that issue this security are those that have a higher payoff under the equilibrium notion. But here, there is a little bit of circularity. I'm sure that this is dealt with properly, because on the one hand, the optimal strategy minimize their expected utility under the set BS, but the set BS is defined based on the equilibrium payoffs themselves. So I need to understand this a little bit better. The complication here is the following. So when I see this offer S, is this part of an equilibrium or not? So the equilibria here, they have to be partially pooling. There cannot be separation, because there is separation. I learn everything about it, has to be known. So uncertainty goes away. So if this partially pooling, if this strategy is part of this equilibrium, then I have to use the equilibrium strategy, it could be mixed strategies, in order to form my set BS. And here I don't see exactly how this is done. Almost done here. If it is an out of equilibrium strategy, then so a strategy is not played in equilibrium, then I see more the use of this restriction, and this becomes equivalent to the refinements that we know in the context of expected utility. But I hate to see a notion of refinements when we have to make a notion of equilibrium itself. So I would like to understand this a little bit better. Is this necessary? Now, one of the lemmas says that we can define equilibrium without reference to the set BS. Maybe we should just drop this. I don't know. Anyway, so let me conclude. I want to say a word about smooth ambiguity. Let me, in the interest of time, not say that. So this is a very interesting paper. So that's me very clear about that. And it raises, addresses very important fundamental questions that we need to address in order to move up further. And it's a very important starting point in making us understand how to model asymmetric information under uncertainty. I think that we still need to push the envelope. Perhaps there are two papers here. One paper is the notion of equilibrium, and a paper is the application to security design. But certainly, it's something that I look forward to see progress on this, because we need these tools in order to push this agenda further.
Thank you.